The reaction you just observed is an example of something called a redox reaction. The word redox is actually a very old word, and it is a combination of two other words, reduction and oxidation. This particular concept or type of reaction has very old origins, and initially its origins were based on oxygen in particular, hence the term oxidation. For example, in olden times, if we had iron bound to oxygen, what we would have to do is combine it with something that took away that oxygen, like carbon. And that would end up with the carbon binding with the oxygen, giving you carbon dioxide, and the iron ending up on its own. As a result, you'd end up with pure iron and carbon dioxide. If I balance this equation out by putting 2's there, I now have a fully functional equation. This particular type of reaction was an older example of a redox reaction. And two things are happening in this case. Iron is losing oxygen and carbon is gaining oxygen. And this is how redox was defined. So old definitions defined redox as the loss or gain of oxygen. So for example, in this case, iron is losing oxygen. So we can say that Fe into FeO is being reduced. In the same way, we can say that carbon is oxidized. So in that way, we defined each of these as being either oxidized or reduced based on what's happening in terms of oxygen. This definition, however, had a lot of limitations. It only really applied to certain reactions. So over time, this definition changed, and we started to look at redox reactions in terms of electrons in particular. So as the definition of redox evolved, we started looking at electrons. And that's what we're going to do, and go back to the example you just saw. In the example you saw, you reacted some zinc with some copper sulfate to give you zinc sulfate and copper. Now, if we look a bit deeper at this reaction and see what's happening, zinc, when it starts off, is technically neutral, right? Because it's by itself. In a neutral form, zinc has 2 valence electrons in its outer shell. Copper, on the other hand, is charged. It's got a charge of +2. For them to swap over in this manner, the only way that a swap can happen is if zinc's electrons were transferred to copper, and in exchange, zinc ended up as +2, and copper ended up with those 2 valence electrons. Remember, when things are charged, they've either gained or lost valence electrons. And if they're positively charged, they've probably lost. So zinc has lost some electrons, given them to copper. And in this case, we've seen an electron transfer. Electron transfer indicates a redox reaction. So redox is now defined as electrons being lost or gained. Specifically, reduction is considered to be the gain of electrons, which annoys a lot of people because the terminology just doesn't match. Reduction is a gain. But in terms of electrons, yes, when something is being reduced, it is gaining electrons. On the flip side, oxidation is defined as a loss of electrons. So in the example down the bottom here, we can say zinc is oxidized. And copper, specifically copper 2+ in CuSO4, is reduced. So copper 2+ is gaining those electrons, zinc is losing those electrons, and you are ending up with an electron transfer reaction, which as a whole gives you a redox reaction. Now, it's important to note that reduction and oxidation don't happen on their own. for something to get reduced, something else has got to be oxidized. If something is losing electrons, something else has to be gaining those exact same electrons. So we see both together. They go hand in hand. What we're going to be doing in this topic is looking at some electron transfer reactions. From this point on, we define redox as electron transfer. And when we do that, this definition becomes really useful and we can analyze a wider range of reactions. There are numerous examples of these electron transfer reactions in our day-to-day life, but two in particular we can look at are the corrosion of metals and a process called respiration. When metals corrode or rust, which is a specific type of corrosion, they generally come in contact with some environmental factors or other chemical substances and they wear down. This wearing down is normally as a result of a redox reaction. Iron, for example, when it loses electrons and becomes an ion, it wears away at the structure of that metal substance, and that is an example of a redox reaction. Those electrons are normally transferred to something else like oxygen, which when present speeds up the process. On the flip side, we also have electron transport reactions happening in our body at any given time in a process called respiration. What happens is we have a buildup of electrons, normally on certain parts of our cell. Our cell has this thing called membranes, and then within that we've got something called a mitochondria, which also has a membrane. And we end up with a buildup of electrons around particular areas of the mitochondria, which turns it into a giant battery, basically. These electrons then transfer from substance to substance, and as they do, they generate some energy, and particularly towards the end, they generate a lot of energy in the form of ATP. So in this way, electron transport reactions or electron transfer reactions, redox reactions, allow energy to be released from stored substances. So if we return to the content side of things, we established in our previous example that zinc is being oxidized. And this is because it is losing electrons. In the same way, copper 2 plus is gaining electrons and being reduced. The easy way to remember this is by using an acronym, and that goes like this. Oxidation is loss of electrons, so we call that oil. And reduction is gain of electrons, which is abbreviated to Rig. So oil rig. So oxidation is loss of electrons, reduction is gain. You can use this to remember what's going on. We're going to take this one step further and bring in a little bit more terminology, and those are the words reductant and oxidant. So zinc is here losing electrons, right? It's being oxidized. If zinc is being oxidized, zinc is kind of allowing copper to be reduced. By being oxidized itself, zinc is allowing copper to later be reduced. So in a way, zinc could be considered to be a reducing agent, or also known as a reductant. By getting oxidized itself, it enables something else to be reduced. So zinc is a reducing agent because it is being oxidized. Think of it this way, a towel. A towel is a drying agent. But what happens to a towel when it dries someone? The towel itself becomes wet. In the same way, zinc, when it reduces something else, it itself becomes oxidized. On the flip side, copper is gaining electrons, becoming reduced. So copper 2 plus could be considered to be an oxidizing agent. Or an oxidant. This is terminology we will come back to later on. So in the weeks to come, we're going to be using a few different tools. We're going to be using oxidation numbers, half equations, and reduction potentials. The first of these is oxidation numbers, and that's what we're going to do in our next lesson. We're going to learn how to use each of these tools to make sense of this topic and also what we do with it. From there, we're then going to encounter a few different concepts, some of which we've already looked at. The concepts of reduction and oxidation, reductants and oxidants, and also spontaneity of reactions, how spontaneously they happen. Finally, we're going to cap this all off by looking at types of cells. We have two types of cells we look at in this topic. They're called galvanic and electrolytic cells, and that'll be the last thing we do in this topic.